Imagine a quiet day at a US Navy test site in Virginia. The air is still, the sky is clear. Suddenly there's a sound. It's not the familiar boom of a cannon. No, this is something else entirely. It's a sharp, violent crack like a colossal whip snapping through the air, followed by a low, humming sizzle that seems to vibrate in your very bones. This isn't your granddad's artillery. This is the sound of the future arriving at 7 times the speed of sound. On the test range, a massive, blocky contraption sits, looking more like a piece of industrial machinery than a weapon. There's no smoke, no fiery explosion from a muzzle, just that incredible, ear-splitting crack and a flicker of movement too fast for the human eye to properly register. What just happened? A 23-pound chunk of metal, a projectile that looks like a giant aerodynamic dart, has just been thrown downrange with terrifying force. It left the barrel traveling at over 5,600 miles per hour. Let me say that again because it's brilliant. 5,600 miles per hour. That's fast enough to get from London to New York in about 35 minutes. All of this power, all of this speed was generated not by a single grain of gunpowder, but by a monumental surge of electricity. This is the pure, raw, and slightly bonkers world of the electromagnetic railgun, a weapon that promises to completely rewrite the rulebook on modern warfare. The projectile itself, now a blur of hypersonic metal, streaks across the sky. It doesn't carry any explosives inside it. It doesn't need to. At these ridiculous speeds, the sheer kinetic energy is the weapon. Think of it like this. If you drop a small pebble, it doesn't do much. But if you could throw that same pebble at the speed of a meteor, it would hit with the force of a bomb. That's the principle at work here. The energy of motion, pure and simple, becomes an unstoppable force. The target, a thick slab of reinforced steel miles away, doesn't stand a chance. It's not just punctured, it's obliterated in a shower of molten metal. This scene, which has played out in real life, is not science fiction. It's the result of decades of research and billions of dollars of investment by people who believe that the age of chemical propellants, gunpowder, and its modern cousins is coming to an end. They are betting on a future where battles are won not by the biggest explosion, but by the fastest projectile. It's a future powered by colossal capacitors and guided by computers, where the fundamental forces of the universe are harnessed to create the ultimate kinetic weapon. And honestly, as a piece of engineering, it is absolutely spectacular. The scale of the power being controlled is just mind-boggling. Right, let's get our heads around this. What exactly is a railgun, and how is it different from the guns we're all familiar with? For centuries, since someone first packed black powder into a tube, the principle of a gun has been the same. You take a chemical, you set it on fire, it creates a rapidly expanding gas, and that gas pushes a bullet or a shell out of a barrel. It's a controlled explosion, really. Whether it's an old musket or a modern tank cannon, the basic idea is a bit like popping a cork from a bottle, just with a lot more fire, noise, and intention. It's a brilliant system that has worked for a very long time. A railgun, however, throws that entire concept in the bin. It looks at the chemical explosion and says, that's a bit old-fashioned, isn't it? A bit messy. A railgun uses no gunpowder, no explosives, no chemical propellants of any kind. Its fuel is pure, unadulterated electricity. Lots and lots of it. Think of the power needed to run a small town, all unleashed in a fraction of a second. This makes it fundamentally different. Because it's not limited by how fast gas can expand, it can achieve speeds that are simply impossible for a traditional gun. It's the difference between a hot air balloon and a fighter jet. This difference is the key to everything. Conventional guns have hit a bit of a wall. You can only pack so much propellant behind a shell, and you can only make the barrel so strong before you reach the physical limits of your materials. The projectile can only go so fast. Railguns, on the other hand, are just getting started. Their speed is limited only by how much electricity you can generate and how well you can manage the immense forces involved. This opens up a whole new world of possibilities. You're no longer just lobbing a shell over a hill, you're firing a metal spear at hypersonic speeds over incredible distances. So in short, a normal gun is a chemical-powered machine. It's an engine that uses a contained explosion to do its work. A railgun is an electrical machine. It's a massive linear electric motor where the projectile itself is the moving part. This shift from chemistry to physics, from bangs to volts, is what makes the railgun such a revolutionary piece of kit. It's a complete change in thinking, a leap into a new technological era where the rules of engagement are about to be rewritten by the laws of electromagnetism. And that, frankly, is incredibly exciting stuff. Okay, so how does this magic actually work? Let's break it down. And please don't actually try this at home. You'd need a power station and a very, very understanding insurance company. At its heart, a railgun is surprisingly simple in concept. You have two parallel metal rails, which is where it gets its name. These rails are connected to a massive power source. When you're ready to fire, a conductive armature is placed between the two rails. This armature is what holds the projectile, or in some designs, it is part of the projectile. It completes the electrical circuit, like flipping a giant cosmic light switch. Now for the fun part. The moment the circuit is completed, a colossal amount of electrical current flows from the power source down one rail, across the armature, and back up the other rail. This creates an incredibly powerful magnetic field. It's the same basic principle called the Lorentz force that makes an electric motor spin. But instead of making something spin in a circle, the magnetic field here is arranged to create a massive forward-pushing force. The magnetic field generated behind the armature shoves it forward with unbelievable violence, accelerating it down the length of the rails at a staggering rate. Think of it like squeezing a wet bar of soap. If you squeeze it between your fingers, it shoots forward. In a railgun, the magnetic field is doing the squeezing and the projectile is the bar of soap. But the squeeze here is one of the most powerful electromagnetic events created on Earth. The projectile goes from a dead stop to several times the speed of sound in the blink of an eye, all while contained within the barrel. It's a pure conversion of electrical energy into kinetic energy, the energy of motion. No fire, no bang, just raw electromagnetic force. The whole process takes just a few milliseconds. A huge bank of capacitors, which are like super fast batteries, dumps all its stored energy into the rails in one gigantic pulse. The projectile is launched, the circuit breaks, and the system immediately begins recharging for the next shot. It's a beautifully elegant, if terrifyingly powerful piece of physics in action. You're literally using one of the fundamental forces of the universe to throw a piece of metal faster than anything has ever been thrown before. It's less of a gun and more of a linear particle accelerator, but for things you can actually see. So why go to all this trouble? Why replace something as proven as gunpowder with this complicated electrical beast? Well, there are three massive advantages that make military planners very excited indeed. The first one is the most obvious: speed, or to be more technical, velocity. As we've said, railguns can fire projectiles at speeds over Mach 7. That's more than 7 times the speed of sound. A shell from a top-of-the-line naval gun might travel at Mach 3, which is already fast. A railgun projectile is more than twice as fast, and it travels on a much flatter, straighter path, making it far more accurate over long distances. The second advantage comes directly from that incredible speed kinetic energy. An object's kinetic energy increases with the square of its velocity. What that means in simple terms is that if you double the speed, you quadruple the impact energy. So a railgun projectile traveling at such hypersonic speeds doesn't need to be filled with explosives. It hits with so much energy that it punches through hardened steel like it's wet cardboard. This is a huge deal. It means you can destroy a target with just a solid lump of metal. This makes the projectiles safer to handle, store, and transport because they are completely inert until the moment they are fired. And that brings us to the third big win cost. A modern guided missile can cost over $1 million per shot. A single large caliber shell for a naval gun can cost thousands. A railgun projectile, because it's basically just a cleverly shaped lump of tungsten and some electronics, is estimated to cost around $25,000. That's a massive price difference. A warship could carry hundreds or even thousands of these projectiles for the same cost as a few dozen missiles. This changes the economics of warfare completely. You can afford to fire more shots, engage more targets, and you won't go bankrupt defending your fleet from a swarm of cheap drones. So you have a weapon that fires a projectile that is faster, hits harder, and costs a fraction of the price of existing munitions. The projectiles are safer, you can carry more of them, and they can reach out and touch an enemy from over 100 miles away. When you put all of that together, you can see why the US Navy and other military forces around the world are pouring so much money and effort into this technology. It's not just a slightly better gun, it's a potential game changer that promises to make ships more lethal, more defensible, and more cost-effective. It's a triple threat. Okay, so this isn't just theory and clever diagrams. There is real-world footage of these things in action, and believe me, it is properly dramatic. The videos released by the US Navy from their test facility are just, well, astonishing. You see the massive railgun, a beast of metal and wiring, just sitting there silently. Then with that signature electrical crack, a projectile is launched. In the high-speed, slow-motion replays, you can actually see the air around the projectile turning into plasma. The friction and speed are so intense that the air itself is superheated into a glowing, fiery sheet. Honestly, it looks like a miniature meteor being born. The impact tests, they are even more spectacular. In one famous test video, a railgun projectile was fired at a stack of 3 thick steel plates, the kind of material you might use to build a warship or a tank. The projectile, which again contains no explosives, arrives in just a blur. The moment of impact is just total devastation. It doesn't just punch a hole. The sheer energy transfer causes the steel plates to shatter and explode outwards in a starburst of white-hot metal fragments. It looks for all the world like a bomb has gone off, but it's pure kinetic energy doing all the work. It's a brutal demonstration of physics. In other tests, they've shown the potential for accuracy. Firing from miles away, the projectiles can actually be guided to hit specific targets with pinpoint precision. This is crucial. It's no good having a fast projectile if you can't hit anything with it. But by combining the hypersonic speed with in-flight guidance systems, the railgun basically becomes a long-range sniper rifle for battleships. The projectile travels so fast that it gives the target very little time to react, move, or even try to shoot it down. By the time you hear the sonic boom of its arrival, you've already been hit. These tests prove the concept works. They show that the velocity is achievable, the energy is just devastating, and the potential is totally real. Of course, these are carefully controlled experiments in a laboratory setting. Firing a weapon on a calm day on land is one thing. Putting it on a ship that is rolling in the ocean, covered in salt spray, and being shot at is another thing entirely. But the test footage really gives us a tantalizing glimpse of the future. It's raw, unedited power, and it shows that the dream of an electromagnetic weapon is well on its way to becoming a terrifying reality. Now, if railguns are so brilliant, why isn't every battleship in the world already bristling with them? Well, as with any groundbreaking technology, there are some colossal challenges to overcome. The biggest hurdle is power. And I mean, like, to fire a railgun requires a truly staggering amount of electricity. We're talking about tens of megawatts delivered in an instant. Most current warships simply don't have the electrical generation capacity to power one of these things, let alone fire it multiple times in a battle without causing a ship-wide blackout. New ship designs, like the Zumwalt-class destroyers, were built with this kind of all-electric future in mind. But retrofitting older ships is a massive engineering problem. The second major headache is wear and tear. The forces inside a railgun barrel are, honestly, biblical. You have the projectile physically scraping against the rails at hypersonic speeds, plus an intense electromagnetic field and temperatures hot enough to melt steel. This combination is incredibly destructive to the rails themselves. In early tests, the rails were so badly damaged after just one shot that they had to be replaced. They've made huge progress with new alloys and materials and can now get dozens or even hundreds of shots from a single barrel. But it's still a long way from the thousands of rounds a conventional gun barrel can handle. Then there's the issue of heat. All that electricity surging through the system generates an enormous amount of waste heat. Firing a railgun once is one thing, but firing it repeatedly in quick succession, as you would need to in a real battle, creates a massive cooling problem. The whole system, from the power converters to the barrel itself, can overheat and fail. Developing a cooling system that is robust enough to handle rapid-fire scenarios, yet compact enough to fit on a warship, is one of the trickiest engineering puzzles they are trying to solve. You can't just slap a giant radiator on the side of a destroyer. These three challenges, power generation, barrel longevity, and heat management, are kind of the holy trinity of problems that have kept the railgun in the prototype stage, They are not impossible problems to solve, but they require serious breakthroughs in material science, electrical engineering, and thermodynamics. The US Navy has even shifted some focus away from the railgun itself to develop the hypervelocity projectiles for use in existing powder guns as a sort of stepping stone. The road to making the railgun a practical, reliable, and battle-ready weapon is still a long and very, very expensive one. While the railgun gets a lot of headlines, it's important to remember it's not the only futuristic weapon being cooked up in the world's defense labs. It's part of a whole family of new next-generation technologies that could change the face of conflict. One of its close cousins is the coilgun, or Gauss gun. A coilgun also uses electromagnetism to launch a projectile, but it does it in a different way. Instead of two rails, it has a series of electromagnetic coils arranged along the barrel. By switching these coils on and off in a precise sequence, they create a moving magnetic wave that pulls the projectile along and accelerates it. Coilguns have a big advantage. The projectile never touches the barrel. It's levitated magnetically. This means there's no friction and virtually no barrel wear, which is the railgun's biggest weakness. However, coilguns are generally more complex and so far haven't been able to achieve the same jaw-dropping velocities as railguns. Then you have a completely different approach to directed energy weapons, which basically means lasers. Instead of firing a solid object, you're firing a beam of pure light. Lasers travel at, well, the speed of light, making them impossible to dodge. They are perfect for shooting down drones, missiles, or small boats, literally burning them out of the sky or water. Beyond that, you have the realm of hypersonic weapons. These aren't guns at all, but missiles that travel at speeds above Mach 5. Unlike a ballistic missile that goes way up into space and comes back down, hypersonic missiles can fly within the atmosphere and maneuver on their way to the target. This makes them incredibly difficult to track and intercept. Countries like Russia, China, and the United States are all in a race to develop these weapons, which could potentially render many existing missile defense systems obsolete. They combine the speed of a ballistic missile with the agility of a cruise missile. So the railgun isn't being developed in a vacuum. It's competing for funding and attention with lasers that offer pinpoint accuracy at the speed of light, coilguns that promise better reliability, and hypersonic missiles that offer unstoppable long-range strike capabilities. Each technology has its own strengths and weaknesses, and its own best use case. The future battlefield will likely see a mix of these systems working together. A warship might use lasers for close-in defense, railguns for medium-range bombardment and missile interception, and hypersonic missiles for striking high-value targets hundreds of miles away. It's a whole new toolbox of technological terror. If and when railguns are perfected and deployed, they won't just be a new toy for the military. They have the potential to fundamentally change strategic thinking. At sea, a fleet equipped with railguns would have a massive advantage. A single destroyer could lay down a barrage of fire equivalent to a whole squadron of bombers, striking targets over 100 miles inland with cheap hypersonic projectiles. This long-range naval gunfire support is something navies have wanted for decades. It would allow ships to influence land battles from a safe distance, without risking expensive aircraft or missiles. One of the most promising applications is missile defense. Intercepting a modern ballistic missile is incredibly difficult. It's often described as hitting a bullet with another bullet, but a railgun changes the maths. It fires a projectile that is cheaper and much faster than a traditional interceptor missile. A ship could fire a volley of these guided projectiles to create a defensive wall, overwhelming incoming enemy missiles with multiple high-speed impactors. This could form a protective shield for aircraft carriers or even entire countries, making them far less vulnerable to attack. It turns defense into a much more affordable and effective game. But the thinking doesn't stop at warfare. The core technology of the railgun, electromagnetic launch, has some incredible potential for peaceful uses. The biggest one, space launch. Getting things into orbit is fantastically expensive, mainly because you have to build a giant disposable rocket full of explosive fuel for every single launch. What if you could use a massive railgun, perhaps built on the side of a mountain, to hurl a payload into the upper atmosphere at hypersonic speeds? The payload could then use a small rocket motor to circularize its orbit. This could slash the cost of putting satellites, supplies, and maybe even people into space. This idea, known as a mass driver, has been a staple of science fiction for years, but the development of military railguns brings it a step closer to reality. It could open up space exploration and commercialization in a way we can only dream of today. Imagine launching a satellite for the cost of a railgun projectile and some electricity, instead of hundreds of millions of dollars. It's a radical idea, but the physics is sound. The same technology designed to create the ultimate weapon could also become our most powerful tool for exploring the final frontier. It's a fascinating duality. So there you have it, the electromagnetic railgun. It's a weapon that swaps the chemical fury of gunpowder for the clean, silent, and infinitely more powerful force of electromagnetism. It's a testament to human ingenuity, a machine that pushes the boundaries of material science, electrical engineering, and pure physics. We've seen how it works, using a colossal jolt of electricity to create a magnetic field that launches a simple piece of metal at speeds that were once thought impossible. It's a concept of beautiful, brutal simplicity, wrapped in some of the most complex engineering on the planet. We've looked at the incredible advantages it promises. Projectiles that fly faster, hit with more devastating kinetic energy, and cost a fraction of today's smart weapons. We've seen the real-world test footage where solid steel is turned into shrapnel by nothing more than the energy of motion. But we've also seen the immense hurdles that still stand in the way. The insatiable thirst for power, the self-destructive forces that tear the barrel apart, and the monumental challenge of keeping it all cool under pressure. These are not small problems, and they are the reason the railgun remains a tantalizing weapon of tomorrow. The railgun is a signpost, pointing to a future where the nature of warfare itself is changing. It exists alongside other mind-bending technologies like combat lasers, intelligent coilguns, and unstoppable hypersonic missiles. These aren't just incremental improvements on old ideas, they are revolutionary leaps that will force military commanders to throw out the old playbook and write a completely new one. The battles of the future might be fought at longer ranges, at higher speeds, and with a level of precision and lethality that is hard for us to even comprehend today. So the next time you see a thunderstorm and witness the raw power of a lightning strike, just take a moment. Imagine harnessing that kind of energy, focusing it, and using it to propel an object at 7 times the speed of sound. That is the promise of the railgun. It's more than just a new gun. It's a glimpse into a future where the rules are different, the stakes are higher, and the bang is generated not by an explosion, but by the fundamental forces that hold the universe together. And you have to admit, that is just fantastically, wonderfully, and terrifyingly cool.